I'm extremely pleased to be able to introduce Henry Pearson, and pleased that Henry is able to join us today. But I'm going to use a chairman's prerogative to start by telling a little story. And as my friends know, I enjoy telling stories. In about the early 70s, I was asked to lecture 1A in Cambridge, and that was to some 200 students. Now, I can't lecture to 200, that's too many. So I would choose a few people, and I'd really lecture to them, maybe half a dozen in the audience. And I chose one man who sat in the first lecture in the middle of the front row, and I felt fairly sure he'd sit there all the time. And at the end of the lecture series, 24 lectures, he came up to me and said, "I very much enjoyed that lecture series. Thank you very much." And I thought, boy, isn't that wonderful? The guy I chose thanks me. And my ego was just exploding a little bit when he said, "And maybe you know my father, Anthony Pearson." That was Henry. So I taught him how to solve differential equations. He had already followed his father into fluid mechanics. He got his first degree in Cambridge. He then did a doctorate in environmental fluid mechanics at Trinity College, where his father had first been, with Julian Hunt, who many of us know. He moved into technical consulting, and then he even built his own company, typical Pearson imagination. He's had an extensive and distinguished career, and at the moment is deeply involved in the important problem of cybersecurity, much of which he can't tell you about, but it's the little bit he has talked to me about I do find very interesting. He's going to talk to us today, I believe, about the fluid mechanics he was inspired to do by talking with his father, and was inspired at the rather early age, something like 14 or so. And of course, Anthony has had an enormous impact on Henry's career and thinking. And as I showed in one of my slides, he can still outthink and out-talk him, even with his eyes closed. But Henry, we much look forward to hearing from you now.
So good morning, everybody. And thank you very much, Herbert, for that wonderful introduction. I do indeed remember your Part 1A lecture course with great fond memories. It's great to see a number of old faces or a number of old names in the list of participants, some of whom I haven't been in contact with for a very long time. So let me just say something for those of you who are wondering about the backdrop slide to me today. This is a golf course in Mexico, which is a nice place to go and spend a little bit of time in very cold weather here. The relevance of golf will become clearer towards the end of my brief talk. Just say that golf is one of the sports that Anthony has been an occasional participant in. There's almost no sport he hasn't participated in at some point. Herbert, you introduced a number of those sports he's involved in. I think there are a number of other ones he got involved in as well. I was delighted to hear originally about this event happening, and I was very honoured when you and Simon suggested that I say some words on my work with Anthony. And I've interpreted that, thinking carefully about it, as really trying to explain the way in which Anthony, perhaps in some obvious ways and some less obvious ways, has had a critical influence on the way the whole of my career has developed. As you've already said, my starting out was in some ways mirrored that of Anthony's. I was interested in maths from a very, very early age. Although to be fair, I think Anthony let me get on with the details of learning about maths as a student pretty much to myself. He was always available to answer specific questions like, would it be a good idea for me to go to Cambridge to read mathematics? Answer yes. Should I put down to apply to Trinity? Answer yes, nowhere better. And then obviously I followed his steps into the Department of Applied Maths and Theoretical Physics, and even studied, although in a different context, turbulence, which he'd been involved in. And as you've said, after doing a postdoc at Caltech, which my father also had a lot of contacts with, I went into industry as he did, but then I stayed there. This is a very personal thing for me, and I've really enjoyed digging back into some very old archives and reminding myself of things that happened. Now, what I'm going to talk about are three elements which at the suggestion of my father I got involved in. They're all linked to his career in different ways, two relating to very specific pieces of work, but they're all very influential on how I developed. So let me start right at the earliest stage, and this relates very neatly to the talk you've just heard, and this is about going back to Anthony and Chris Petrie's, who I understand is on this talk. They're formative papers on blowing a tubular film, which was published in JFM in 1970. Now, the year before, while this work was being done, as a impressionable 14-year-old, and I think my father thought it'd be interesting to get me involved in something he was doing and interested to get involved in computers. He suggested that during a school holidays, I learn how to program the computer and do some process some experimental results they've got. And they were doing some work on the actual blowing of films. And the thing was that they had a mechanism for printing a sort of ladder marking on the film as it blew up at the top with ink, an ink roller, and then photographing, taking a video film of the markings on the outside of the film. And with a bit of geometry and a bit of computing, that allowed you to actually measure how the film tube was expanding. Now, you will be surprised to see, and this is completely coincidental, the same picture of the famous IBM 1620 computer that Herbert used. Now, I know why that is, because we probably both did exactly the same thing and Googled IBM 1620 images, and this is actually the biggest, highest resolution picture available, and the one actually that most closely resembles, as I remember it, the computer in the Cambridge Chemical Engineering Lab. The only thing I would differ with Herbert's description is that actually in those days it was paper tape you had to feed into it rather than cards. They came a bit later. Anyway, so that was my first introduction to computing at the age of 14, and I loved it and couldn't get enough of computers from then on. So moving on, the next thing I did, and this was 2 summers as an undergraduate, my father suggested that with a bit of help from him that I apply to ICI Plastics Division in Welwyn Garden City, where he'd worked or had been associated with, to offer myself as a vacation student. And actually what I got put to do was to look at something that I don't think my father's ever particularly been involved in, and that's analysing X-ray diffraction data from polythene blends. That I couldn't find a picture to explain exactly what the X-ray diffraction spectra, if you like, look like from these polythene blends. This is showing just slightly different things. This was looking at blends where there were high density and low density polythene, and you were trying to understand something about the structure of it from the X-ray diffraction patterns. And this involved essentially inverting Fourier transforms. Something I learned from that was that actually some of these inverse problems are nastily unstable, and you have to be quite clever about it. So I spent 2 summers doing that. And then finally, the most major thing that I got involved with with my father, and this is where we really did effectively work together, and this was consulting work that he was doing, and by this stage, and we're talking about the mid-70s now, he'd set up as a sideline a small consulting firm consisting of him, and he hired one or two of his co-workers, and in fact he also hired me to work with him while I was a PhD student, and I did a bit of moonlighting from my PhD student. Now, those of you who are golfers among you may know that the Acushnet Corporation is very famous because it makes Titleist golf balls. Golf balls are a massive product around the world. Acushnet and Titleist make some 1 million golf balls a day in 4 plants. These plants are based in New Bedford, Massachusetts, just south of Boston. The picture in the top right here is one of the factories they use. They have factories there, or they did when I was involved in the 70s, which are old cotton mills. Golf ball manufacturers moved on a lot. On the bottom left, you'll see how they used to make them in the 70s, and that's a wound rubber band, essentially very long rubber band that's automatically wound round and round and round, thousands and thousands of towns round what's essentially a liquid core, and then a plastic cover is molded onto it. The modern ones are actually entirely molded in 1, 2, 3, 4 or 5 different pieces. But actually it wasn't really the golf ball manufacturer I was interested in. It was in modeling, in a practical sense, the injection molding of rubber components. The rubber component you can see the picture of in the bottom left-hand corner there is something called a Saginaw boot, which is something that you get in the steering, various parts of the steering of cars. Particularly, I think this is like one that they were working on in Acushnet at the time, because Acushnet, as well as making golf balls, the other half of the business was into molding rubber, starting with O-rings and then moving on to increasingly complex molded rubber components for the car industry particularly. Now, this was the reason for getting involved. Was my father was engaged in doing some consultancy work for the Acushnet company on their injection molding of rubber. And then as this developed, he wrote a paper, which has not been mentioned yet, on variable viscosity flows in channels with high heat generation in 1977. Hilary and John Ockenden, I think Hilary Ockenden's probably on the call also, did some very closely related work that they published at the same time. And Anthony, working with Stephen Richardson at Imperial, took these ideas forward, and Stephen wrote some computer programs to try and use the ideas for the design process for rubber injection molding. What happens in rubber injection molding is you start with rubber pellets, which have been very carefully formulated to meet the requirements of what you're trying to mold. They're then essentially mashed up in a screw extruder. They're heated up to the point where they will flow. They're then under a lot of pressure forced through tubing into the mold. And the actual process of designing that whole system is really quite complex, and at the time involved a lot of trial and error, gut instinct by the engineers. And this was a program to try and understand, taking the most some very advanced work that was going on to understand how better to design these things. So my job was to take some computer programs that Stephen Richardson had written and to actually implement them on the computer systems in Acushnet in the US, and try to work with the engineers there to see how to make them practically useful. That was a fascinating activity over two years or so, on and off, which taught me an enormous amount about the practicalities of trying to apply mathematics in some really quite complex circumstances. And out of this came the one paper you'll see there, which I wrote with my father. So I've gone on probably long enough. So in terms of in conclusion, what did I learn from all this, and how did it affect my career? Well, I certainly gained, and from the earliest involvement with my father, age 14, a lifelong interest in computing and what's now referred to as the digital environment, and that's been a theme on and off throughout my career, and very much so now. What it also gave me was a real understanding of how one could, and the issues in doing so, apply what you might call hard mathematics and physics to messy real world problems. And that's something that I got from Anthony at a fairly early stage of my career. And I think that probably characterizes what's driven him through a lot of what he's done. I also gained a taste for consultancy work, which has been a theme throughout my life, and also an interest in business. And as Herbert said, I left the academic life at a relatively early stage and went into both consulting and building a business. So I think I'll stop there and see if there are any questions.
Well, Henry, thank you very much. Really very interesting, and especially the suggestions of the connections between industry and academia, which your father managed wonderfully and you have also. Are there any questions? Chris Petrie? You've raised your hand, Chris. Would you like to unmute yourself and ask your question?
Right, I have unmuted, I believe.
Yeah.
You can hear me? Yeah, good. Well, two things. First, a comment to say thank you to Henry for correcting the information about the IBM 1620, which I spent an awful lot of time babysitting when I was a PhD student and postdoc. Probably more time than I should have done. I might have done better on the mathematics if I'd. Anyway, the second thing to mention, the fiber spinning problem has always perplexed me in a mathematical sense, because what you have quite clearly is a two-point boundary value problem. You've got initial conditions at the emergence from the die, and you've got a take-up condition. But the equations themselves are evolution equations. So having a two-point boundary value problem for an evolution equation is something I have always found perplexing. And I tried to get my professor, head of department in Newcastle, Alan Jeffrey, interested in this because he was very much into partial differential equations, but I never could get him to sort it out either. So just raising that as something interesting, I think, perplexing.
Henry, would you like to comment?
Well, I see the point. Is it just that it's lucky that the equations work out as they do, and maybe perhaps, I mean, I think physically maybe you can't actually really set the boundary condition at the point where you start the calculation. There will be an upstream influence from the fact you're pulling it from the bottom. So if you measured more accurately, essentially what I'm saying, I think, is that you aren't quite, and I'm going out on a limb here, you may not actually be strictly setting that boundary condition at the top. It's just a convenience to think of the problem like that, and it happens to work out. I don't know, Chris, whether that helps or.
Okay, are there any further questions? Could I just comment on Chris's response to my showing the IBM 1620? I wanted to show a typical card that may not have been used in the 1620, but because just a few weeks ago, when I was Skyping with a very, very clever postdoc, I happened to bring up onto the screen a slide rule. And he said, oh, my God, I've never seen a slide rule before. And I'm sure he would have never seen a card either, a computer card, of which there were thousands. And I cannot but tell you one of my, quote, favorite stories, that a computer programmer at the LMB in Cambridge was fired. This is quite some time ago, clearly. And she thought she was unfairly fired. So she used the key she still had on a Saturday morning, went down to the basement where all the computer programs on cards were kept, and shuffled the cards. Couldn't do that today. Henry, thank you very much for your reflections and insight into your father and his abilities and your own. I wish I'd known how to reply back to you in the early 70s when you said, I know my father. And I should have been able to say, yeah, you know, and we'll look forward in 50 years to having a celebration on his 90th birthday. Well, thank you very much for improving that celebration. We're going to have a short break now for some 10 minutes. So we'll resume at 10 minutes past 12. And I look forward to seeing you all then.